In this video, we will discuss some important parameters related to communication system. So they are channel capacity. We will see what is signal to noise ratio and how it is related to the channel capacity. And then we'll just have a general introduction of modulation and its benefits. So before we understand channel capacity, it's important to understand what is pulse code modulation. So we know from previous information that in order to digitize a signal, the first step is to sample that signal. So the second step is to quantize it. And through this process, we can actually convert an analog communication to a digital communication. So um, now in this figure, we have an analog signal that is represented by the dashed lines. This signal, as we said, is first sampled. So for example, this is a sample of the signal. Now the next step is to divide the minimum and maximum levels of these signals into different levels. So in this case, for example, the total number of levels that we have are 4. So each level is represented by a binary number, a pair of binary number, because for 4 levels we require can be represented by 2 binary numbers. So in pulse code modulation, instead of transmitting this sample, we transmit a code for that sample, which, for example, in this case, this sample is closest to the level 2, so we will transmit a code for this sample, which is 10 in this case. And similarly for this sample, which is close to level 3, we will assign it level 3 and we will transmit a 11 for this sample, right? So in this way, we transmit these binary numbers instead of the actual values of the samples. So this technique is called pulse code modulation. If we have more number of levels, then in this case we can see there is a lot of error between the actual signal and its representation. So if we have, for example, like more number of levels, as you can see here, so then the actual signal and the quantized signal become very close to each other. So the higher the number of levels, the better the approximation is between the quantized and the actual signal. So now this is another figure where we can see the number of levels are large. Now they are, if we count them, so they are around 16 levels. So this is the lowest value and this is the peak value. So between these two, we divide them into 16 levels and they are represented by capital L. The samples are shown here. So for example, this is a sample and we assign each sample, we assign it to a certain level, and then as before we transmit the binary representation of that number, which is over here. So this is how pulse code modulation works. We have, for example, MP is the lowest amplitude that it can go, so minus MP, and MP plus MP is the highest amplitude. So the width of one level is 2 MP divided by L, which is the total number of levels. So this is how the quantization works. Now so this process is also known as analog to digital conversion. So once this analog to digital conversion or AD conversion is over, the original analog message is represented by a sequence of samples, each of which takes on one of the L preset quantization levels. So we have divided them into L number of levels. The transmission of this quantized sequence is the task of the digital communication system. So now the sequence that we have obtained, we just transmit it, and this represents, this is done in a digital communication system. So the technique is called pulse code modulation PCM. It's very simple and yet very common mechanism for digital communication system. So why it is so effective is because if you can see, all we get at the end of quantization is either a 1 or a 0. So we can represent the 1 bits by one pulse P1T, and zeros are represented by another pulse P0T or P0T. So then the receiver only needs to determine if it has received a 1 or a 0, which is relatively quite simple, and then at the receiver the opposite of this process is done to get the analog signal, right? So the number of levels, if it's 16, the number of levels are always a power of 2. So that means that we would require 4 bits to transmit one sample. So if we require, let's say, if we want to increase the number of levels, the signal quality will be better, but then we would require more bits per sample. So this is a plot, this is a table which shows how these numbers how these levels which were previously in decimal numbers from 0 to 15, the binary equivalent is shown in this column, and the pulse coded waveform is shown in this column. So we can see that for a 0 a negative pulse is transmitted, and for a 1 a positive pulse is transmitted. So this is why the technique is so simple and effective, because the receiver only needs to detect if it's a positive pulse or a negative pulse, and it can extract all the information from that. So now what is in this scenario, what is the role of bandwidth and power of the signal? Now first thing is the bandwidth of a channel. So what is the channel bandwidth? Basically it's the range of frequencies in which a signal a signal can be transmitted. Yes. So why do we have a range of frequencies? Why cannot just any frequency be transmitted over the channel? So this is a plot. The source is shown here. So on x-axis we have the frequency, on the y-axis we have attenuation. So as you can see, in this region the attenuation is the lowest. And even we can have frequencies in the range of like 1 gigahertz, which is generally used for the GSM communication. So this is the region where the frequency and where the attenuation is lowest. So this is the desirable region for transmission of data, and that is why this region is generally licensed by the government to network operators. The region beyond this is, the attenuation is very large, so it's not useful for the network operators. So this is the channel bandwidth, or channel, we can call it channel bandwidth. The capacity is going to be related to this bandwidth, as we'll see, in the coming slides. So if now this is the bandwidth of the channel. Similarly, we can have bandwidth of signals as well. So it measures the maximum range of its frequency component. So the faster a signal changes, the higher maximum frequency it has, and larger would be its bandwidth. A signal can be sent successfully over a channel if the channel bandwidth exceeds the signal bandwidth. So the channel bandwidth is like a pipe, and or it's like for example a road, and the signal bandwidth is the number of cars that can be transmitted in parallel through this road. So if we have a 2-lane road, then we can only pass 2 cars, or we can also pass 1 car. So in that case, the channel bandwidth exceeds the signal bandwidth. So if we transmit 2 cars, then the channel bandwidth and signal bandwidth are equal. And if in a 2-lane road we are passing 3 cars, then that would not be possible, because signal bandwidth in that case would be larger than the channel bandwidth. Now how are they related? So let's say if we have channel bandwidth of B, it can transmit n pulses per second. Then to transmit kn pulses, we need to have a bandwidth of kb. So the number of pulses per second that can be transmitted over a channel is directly proportional to the bandwidth of the channel. So the pulses per second that we generate as a consequence of pulse code modulation, they are they are related, directly proportional to the bandwidth of the channel over which we are going to send them, so, or transmit them. So for example, compressing a signal in time by a factor of 2 allows it to be transmitted in half the time, right? So if we have a pulse like this pulse modulated system, if we compress this pulse, we let's say we are sending a narrower pulse, then we will have more space for further pulses, so the data rate can be increased. But the issue is, when we make the pulse narrow in time, the bandwidth in frequency is increased. So if the compression of the pulse is by a factor of 2, the bandwidth increases by twice. So there is always a trade-off between these two quantities. Now signal bandwidth and power. So signal power is related to the quality of transmission. If we have a higher signal power, the noise effect is and interference effect is much lower. To determine this, a quantity is defined which is called signal to noise ratio. It's very commonly used and it is specified for each communication system. A certain minimum SNR at the receiver is required for the receiver to detect the incoming signal and demodulate it. So larger signal power allows the system to maintain this minimum SNR required for proper working of the communication system. Now, what is channel capacity and the data rate? So remember, channel capacity is related to the channel over which the signal is transmitted. So for example, this could be a wireless channel, a fiber channel, or something like that. And the data rate is the it's the number of bits, it's the data rate of the signal that is to be transmitted over the channel. So this channel capacity must be larger than the data rate in order for the system to work properly. Now channel bandwidth limits the bandwidth of the signals that can successfully pass through it. So signal SNR at the receiver determines the recoverability of the transmitted signals. Higher SNR means that the transmitted signal pulse can use more signal levels. So this is important. We can increase the number of, we can transmit more bits by increasing the number of levels along the vertical axis. So but that was only allowed if we have a higher SNR. In other words, if we have a lower noise, right? So high bandwidth also means that one can transmit more pulses, faster variation over the channel. So some examples of more signal levels are given on this slide. So for example, in this case, from this point to this point, we have a single pulse. This is the eye diagram of a non-return to zero signal. So for example, a 1 is represented by this pulse and a 0 is represented by no pulse. So the receiver can detect if a 1 or a 0 was transmitted. Now if you want to increase the bit rate, what we can do is we can increase the number of levels. So let's say we can say this is for 0 0, this is for 0 1, this is for 1 0, and this is for 1 1. So in this way we are by keeping the same pulse width, we are transmitting more bits per second. So this is, the data can be increased, right? Now what we can do, there's another scheme that's called, this is called PAM4. We have another scheme which is called PAM8 because it has 8 number of levels, and so we can transmit 3 bits at a time in this case. So we can transmit, let's say 0 1 0, 3 bits in this case at a time. That means for the same bandwidth, because the pulse shape is the same, we are having the same frequency components in the frequency domain, we are able to transmit more data per second. But again, there is another thing, there's a catch in this. We can only do this if we have a good SNR of the channel. So that means the noise in the channel is low. So what we can conclude from this is that if we want to increase the data rate, if we want to transmit more bits per second, we have to that is only possible if the noise in the channel is low, so the SNR of the system is high. So that means channel capacity and SNR are related, and yes, indeed, they are related through a function, through a formula that is for the channel capacity. um, that formula assumes that channel has noise as well. It's called additive white Gaussian noise, AWGN. It's called white noise because um, it spectrum is quite broad. It is distributed over a wide range of frequency. So just like white light, which has all the frequencies or wavelengths, it's called white noise. It's called Gaussian because it has a shape like this, almost a Gaussian shape. This is the assumption while deriving this formula for channel capacity. It's called the Shannon's equation. So here, this is the capacity, this is the achievable bit rate that we can have. This is the maximum bit per second that we can transmit over a channel that has a bandwidth of B, and it has a signal to noise ratio SNR. So according to this formula, this gives us the maximum bits per second that can be transmitted under a certain value of SNR and under a certain channel bandwidth. So as you can see, this is quite an important formula as it gives us the the maximum possible rate. So the next thing is modulation and detection. So it's again, modulation is an important technique related to communication. Why do we need modulation? So first of all, as we know, we perform analog to digital conversion to get digital signals. Now the signal that we achieve, so for example in analog communication, the message signal is our voice signal. In digital communication, the message signal is the voice signal or the analog signal converted into a digital signal in the form of bits. Both these types of signals are called baseband signals because they have not yet been transmitted over the channel. They have not yet been used to modulate any high frequency signal. So when signal and channel frequency bands do not match exactly, channels cannot be shifted. Messages must be shifted to the right channel frequency band. Now, as we saw in this figure, that the frequency, let's say the voice, they are very low. They are in kilohertz, and the channel capacity, the channel's response in this region is very good. It has low attenuation response in maybe some other frequency window. So how do we shift this signal? How do we shift this baseband signal to the desired frequency? So that is done through modulation. So what happens in modulation is the baseband signal is used to modify or to modulate some parameter of the radio frequency carrier, which is a high frequency carrier, and the frequency it is chosen, the frequency is chosen based upon the channel response, right? So if the channel response is it has low attenuation at a certain frequency, so we choose that RF signal or RF frequency to transmit our data. So we can either vary the amplitude of the signal, the RF carrier, by the data, or we can use this data, the baseband signal, to vary the frequency or phase of the RF carrier. And so based upon that, we can have AM, FM or FM, the frequency modulation, and all these different techniques. Right, so this figure gives us, a visual representation of different modulation schemes. So in A, we have a carrier. This is the high frequency carrier. Again, the frequency is chosen based upon the channel response. So we choose the frequency which has lowest attenuation, which is attenuated by a relatively lesser amount compared to other frequencies by the channel. So this is the baseband signal, so which is the modulating signal. In this case, we have chosen a sinusoidal signal as the baseband signal. just for illustration. Now this is an example of an amplitude modulated signal. So you can see the baseband signal modifies the amplitude of this carrier, and this is an example of frequency modulation, where you can see the baseband signal modifies the frequency of the carrier depending upon the amplitude of the baseband. So now this plot shows us the another benefit of modulation. That is, as you can see, the signal is first, the signal is to be transmitted is inside a conductor. In that case, it is called a conduction current. Then this signal is, it appears, because it's a sinusoidal signal, when it is having a maximum value at one terminal, it has the lowest value at the other, the negative value at the other terminal. And so this positive and negative creates a sort of electric field between the two poles. So this is like a dipole antenna. This electric field is variable, so it generates a magnetic field, and so the signal is transmitted in the air as an electromagnetic wave. Now, as you can see, for maximum transmission, when this part is maximum, this part is negative minimum. So the distance between these two is exactly equal to half of the lambda. So the size of the antenna should be half of the wavelength. Now, for efficient transmission, now if we consider a message signal, let's say a voice signal that is at around 3 kilohertz, such a signal will have a very high wavelength. It will have a wavelength in kilometers, and so the antenna that it would require to be transmitted would also be in kilometers, right? So this is not practically feasible. So this is another benefit of modulation, that if we are using carriers that have frequencies in megahertz and gigahertz, the size of the antennas can be very small. So for example, for 10 megahertz, the size of the antenna from the equation of lambda by 2 would only be 30 meter. For 100 megahertz, it's only 3 meters, and for gigahertz, which is generally used in the GSM communication, the size would be in centimeters. This was one benefit of modulation, that we can perform efficient radiation of the signal. The second benefit is multiplexing. Multiplexing means we transmit multiple signals at the same time, and all of them are at different frequencies, and so they do not interfere with each other. So we can have multiple TV channels, and they all use this multiplexing technique. Now this is an example of a frequency division multiplex signal. So this has a separate baseband signal, this is another baseband signal. All these baseband signals inside these channels have the same frequency range, but the modulating signal, the carrier, the RF carrier of all of these channels are different, and so they do not interfere with each other, and so they can all be transmitted at the same time. So this is a second major benefit of modulation, right? So various baseband signals modulate different carrier frequencies, thus translating each signal to a different frequencies. If the various carriers are chosen sufficiently far apart in frequency, the spectra of the modulated signals, known as, for example, TV channels, in case of cable TV will not interfere, and so we can tune into the correct channel at the receiver to, and in this way we can get multiple channels for our viewing. Now this technique was called frequency division multiplexing, or FDM. These are some calculations just to show how the modulation works. How the antenna size are related to the modulation. So you can see, if we have a frequency of 3 kilohertz only, then the lambda would be 100 kilometer and antenna size would be around 50 kilometer. And similarly, if we have a 300 megahertz signal frequency, let's say the carrier is of this, RF carrier is of this high frequency, lambda would only be 1 meter and the antenna size required would be only 0.5 meters. So instead of transmitting, we have these three channels that are baseband signals. We can modulate different carriers with them, FC1, FC2, 3, and then we can multiplex them and transmit them at the same time. So in summary, we discussed pulse code modulation, signal bandwidth and power, channel capacity and data rate, modulation, radiation of modulated signals, multiplexing and its benefits.